Okay. So we can create another Python function in here like this one, linear regression .py in here. Okay. And so you must first import numpy function as mp. Okay. Import matplotlib.py plot as plt. Okay. And also import the pandas method, pandas library as pd, because we want to write the whole data into the Excel file. Okay. And so import the TensorFlow as tf to build our regression model. Okay. And firstly we need to set the seed value like this one. For example, mp random dot seed 42. It's the simple syntax. And so we can create the x equal to the mp random dot rand function in here like this one, 100 times 10. Okay. So these are the bases of the data set. If you want to use the simple data set coming from the means or any biomedical signal or image processing, you don't want to use that, because if we don't have any training data set, we cannot set the x and the y. Okay. And so it's the arbitrary set. So we can also add some noises in here like this one, mp random function class with a normal distribution. Okay. 0 and 5, 0 mean and 5 standard deviation number. Okay, sigma values for the 100 points. Okay. And so the simple model is that the 7 times x plus 5 plus noise. Okay. These are the model. And so theta 0 is equal to what? 5, and theta 1 is equal to what? 7. Okay. And so we have the noise value, because the error must not complete all the data to the 0. Okay. Firstly, for your application, scatter plot to visualize all the data, because if you have this model, and so you must visualize your data in order to what? In order to see the proper pattern. Okay. For example, plt scatter is given in here x and y with the label of the data with noise. Okay. And alpha is the opacity rate of our function, and plt plot is given in here x. Alpha is the opacity rate of the R function, which means that if the equals to alpha is to 1, and so your points are solid. But if you are taking the alpha to 0.5, and so it's more something that's white, or it's not solid. Okay, less solid. You can see that. And so x and 7 times x plus 5. These are the model. Okay. And so we can color in the red, and label is equal to the true line. Okay. With the formulation of the the y is equal to 7 times x plus 5. Okay. And so we can add the label in here like this one, the plt x label. So the x and y label is equal to the y. Okay. And plt legend should be calling, because if you are using if you want to use the legend, and then the legend cannot be seen on the figure. Okay. And so plt title is the random data with noise, and so healthy grid is true, and then healthy dot show must be called in here. Okay. And so our model is the what the some base point in here. The true model is in the red line in here, but we have data like this one, the noisy data in here. And so each data with specific y value, x equals to y, and so we can use the supervised learning in here. Okay, but firstly, in order to reach any data in here like this one, the data must be represent the PD or pandas utilization. Okay, data frame can be calling in here like this one with a dictionary operation in here, and so the input values is assigned with x, and x is given in here, and so the output values y is equal to the y. This is the standard definition of the what the dictionary usage. Okay, and so this data can be written to what, to Excel. Okay, it's the name of the Excel, for example, linear regression data XLSX. Okay, and the index notation should be assigned to the false at this case. Okay, and so if I run this code, and then I can create the Excel file with the specific what, for example, with the specific title. Okay, and so our data can be written on this page, and so you can easily store your data by using this term. And so, but how about we can take these values from the what, from this Excel file, and so the loaded data can be defined in here, and so the PD pandas utility can be used with the read Excel file in here like this one, and so the linear regression data XLSX. Okay, and so the dictionary can be given, or this given to this what, the XLSX file, Excel file, and so X can be loaded with the what, with the specific keywords in here, input X. Okay, and Y is the loaded data, and so the output Y. Okay, and then we can reach the whole data from the Excel file. Okay, if you have any data set which is written on the Excel file, you can easily take from this data by using what, the pd.read Excel file. Okay, and so we can print the loaded data like this one, the print loaded data head in here. Okay, and so if I run this code, then the whole data can be easily reached by using this formation. Okay, and so how can we utilize or create the regression model by using the what, the TensorFlow implementation? The TensorFlow can be given by the model is the what, the TF Keras sequential library, and so the Keras is a simple neural network library which is defined in the TensorFlow, and sequential means that we can create the whole model activation function or the output function or the input function by using this sequential form of these things. Okay, and so these parameters are defined with the what, with these terms. Okay, and so we can create this time in here like this one, and so tf also some specific function layers, okay, and the input parameter in here. And so if we have the input in here like this one, we should give the shape of these things like this one, 1 comma empty space, okay. And so which means that the input is defined with what, 1 parameters, okay, 1 parameters. If we have 2 parameters, and the shape function should be equalized to the what, the 2, okay. This the parameters, which means that the what kind of input should be included in your model in here. For example, we have the 1 feature x1, okay, and so if we have the 1 feature, 1 input parameter, shape should be equal to the what, the 1, okay. This is simple. We can define the many layers in here, but we need to add the input and output and the dense layer in here in order to train your network, okay. This is the implementation of the one perceptron, one neuron model, okay. And so which is coming here like this one, the keras layers, the dense or the activation function should be given at this time, okay. And so in the dense function we have one neuron because we have one hyperplane in here, okay, one hyperplane, because we have the one model h theta 0 plus theta 1 dot x, okay. If we have 2 parameters, and so we should give the 2 neuron in here. In neural network we can use the 2 or more in here with the multi-layer. Yes. Mm-hmm. We have the 1 layer. Firstly, we need to shape the input in here, 1 parameter, and so we can add the 1 neuron in here, okay. And so that's all. 1 parameter, 1 base, and so we have 1 neuron, and the output should be given at this time, okay. That's all. That's all. That's all. And so we need to give the some initializer function in here, and tf constant initializer should be given with the parameter of, for example, 1, okay, for the what, the neuron, okay. And so theta 1 should be initialized by using these terms, okay, and also given the what, bias initializer theta 0, which is even what, the tf constant initializer with the parameter of, for example, 1, okay. So if I using these terms, and then this dense function creates the what, creates the linear neuron, okay. If you are using the any sigmoid or tangent function, we should specify as an activation unit in here. In the next example we will use it, okay. And so but this model is sufficient for the what to create the R model in here, because the theta 0 plus theta 1 times x is satisfied in this example, okay. This is the basic building of the what, the neural network model, okay. And so how can we compile this model? Model compile function can be used is in here, and so we need to set the optimizer in here, standard stochastic gradient descent algorithm, which is derived from these things. And so we can easily write the whole the codes theta 0 and theta 1 learning, but in the keras or the TensorFlow we have the some written function, and we can use it, okay. And we should give the loss function in here, like the R cost function, for example, mean squared error function, which is defined in the what, in the slides, okay. And so, to train the model can be given by the model.fit. Okay? And so we should give the input and output, and we should define the epochs in here like this one, 100, and the verbose is equal to the 0. Or the validation process should not be given at this time. Okay? It's the simple parameter. It's the validation process for the verbose system. It's not represented in this case. Okay? But if I need to visualize of all of these things, and so this could be set to another values. Okay? So, and we can get the prediction in here like this one. If the model is fit by using this term, so we can create the ypred value by using the model predict function. Okay? In each case, we should supply the x value. Okay? In here. And so, if I train the model by using this term, and so we can predict the model by using any variable in here like this one. And then I can show the plot value, plotting the whole parameters in here, plt scatter like this one, x and y. This is our what? This is our training data set. And so the label with label is equal to the what data with noise. Okay, and alpha should be set to 0.7 opacity value, and also we need to plot to what the x ypred. This is the output of the our model. Okay, and so we can set the color is equal to the green value. Okay, and the label is regression line, for example, and line width is equal to the tree. Okay, we can visualize all the points in here like this one. Okay, and so that the x label is input x, y label is equal to output. Okay, y, and all the plot legend should be given in here, and the plt grid must be given the true value, and plt show must be called in order to show the whole data set in here, and plt title should be assigned to the linear regression with TensorFlow. Okay, so if I run this code, this is the first basic representation of our algorithms. Okay, and so if I close, and then this TensorFlow core calls CPU to compile the whole codes, and fit function is running on this place. And so in each for iteration we have reached to this value. Okay, this green line is the output of our model. Okay, so we can print or we can define the whole models by using these terms or this code representation, but in the linear relation. If we have the nonlinear relation or the exponential relation or the some complex relation, we should add the more dense function in here or neurons, and then we can represent another functions in here. But in the syntax, in a simple way, we can utilize this code as a basis of the linear regression problem. If you have any data set, you can use this code. Okay, easily implemented. I will share this code in classroom. Okay, so this is this is the simple representation of the linear regression. Okay, but we may have the multiple regression on this place. Okay, So, for the multiple regression, okay, because I need to take this time. And so, in the multiple regression, we may have rule like this one. Multiple regression code includes to what the model parameters like this one: x1, x2, x3, and for example y. Okay, for example 1, 2, blah blah blah, 0, 1, 0, 5, blah blah blah, 100, 105, blah blah blah, and 1, 0, 1, 0, blah blah blah. Okay, and so this data is distributed with the what with many features in here. Okay, and so the model function, we need to take the model function. Which model function is appropriate for this representation? Tell me. It's like you should tell me the theta type in here. For example, theta 0 should be given in here as a bias, and so we have the what? Theta 1 x1 plus theta 2 x2 plus theta 3 x3. Okay? This is the basic representation of this model. And so the cost function should be selected like the what j 1 divided by 2n, because it's the arithmetic mean of the what the total cost function variable in here to n, and so we can say that the y I and theta transpose time x square. Okay, this is the basic representation of this vector notation. That product, yes. And so the training algorithm is simple because we have theta e, and in each iteration we should take this value like this one. Okay, in the multiple regression case we can use this notation. Okay, and so by this time, and then we can create another example in here like this one. So multiple regression .py. Okay, and so firstly we need to import the numpy is here as mp. Okay, import matplotlib py plot as plt. Okay, and so import pandas as pd, import tensorflow stf, and also we need to give the sklearn metrics, import mean squared error, in order to show the performance of the algorithms. Okay, and firstly we need to give the some random seed point in here like this one, 11. Okay, and so generate the x1 and x2 for the multiple regression. For example, x1 is equal to the mp random dot rand 100 point is given in here like this one, and times 10. Okay, x2 is also defined with this notation. Okay, and so we can create some noise in here like this one, noise parameter mp random rand normal, standard normal in here like this one, 0, 5 and 100 data points in here. And so in this case our parameter is equal to 7 times x1, 12 times x2 plus 5 and plus noise. Okay, these are the basic ground truth model. Okay, so firstly we need to visualize all the codes in here like this one. Figure is equal to the what plt times figure, okay, and ax is equal to the fig times at subplot in here 1 1 1. It's the index of our code, and we can give the projection of the 3D, okay, because we have the multiple region in here, and so we should define the multiple regions in here, for example 3D format, okay. And so x scatter can be called in here like this one, x1 x2 and y. The label is equal to the data with noise with the alpha ratio of the what 0.7 opacity of the R code in here like this one, okay. And so the ax set x label like this one, the input x1, and y label is assigned to x2, and z label is assigned to output, okay. So if I want to visualize these things, plot title, which is given in the random data with noise parameter in here like this one, plt grid is true, and plt show must be given at this time, okay. And so if I run this code, and then we have the 3D objects or the plot variation in here like this one with the random data, okay. And so we have the sum generation in here, but in higher dimension for the multiple regression, okay. So we have this information, and then we can create the Excel data file in here like this one. Data pd is a pandas function or the variable. Data frame can be defined with the some dictionary values in here. Input x1 is equal to x1, and we can copy of all of these things in here, and x2 is equal to x2, and output is assigned with the y value, okay. And then we can write the whole data into data to Excel file like this one. For example, multiple regression data xlsx, and index should not be seen on this page, okay. False value is given, okay. And so if I run this code, I have built the regression data, okay, like this one, multiple regression data. And so I can easily take these values from this Excel file, okay. These are the outputs, these inputs, okay. And so we should load the data like this one, pd data or read Excel file in here. So we can give this name like this one, okay. So x1 is load data with with this key, okay. First key. The second key is equal to to x2, and the third key is equal to the output, okay. And so we can assign the y in here like this one, and we can get every data from the Excel file, okay. It's the simple implementation from taking the Excel file or Excel data. And then we can create the R model in here like this one. TF is a tensor file, the library in here, and so we can use the we should use the Keras neural network library, okay. And so we should give the sequential format in here, okay. And so we can give the what the least domination in here, like this one. And now, in the first place, in the previous example, we should give the what the tf keras layers input with the what shape 1. But in this case, shape is equal to the 2. Okay? Because we have the 2 feature. Okay? Please be louder when you're speaking. I don't hear you. We have comma, 2, comma, because we have the many data in here. Because we have 2 feature, but we may have the 100 points to train, or 1 million points. And so I can give the empty space in here. Yes, this is standard notation. It's the empty space. Because we may change the 100 data to train, or the 1 million data can be fed to what? To this model. Okay? So, if we have this term in here like this one, and so we have keras layers dense function in here. For the dense function, we should give the 1 in here because we have the 1 neuron in here. And so the kernel initializer should be initialized with the what the tf keras initializers constant with the parameters of the what the 1.0 1.0 because we have 2 parameters in here. Okay. So for the bias initializer, I'm sorry. Bias initializer, we should use the tf keras initializers dot constant value with the parameters of the what the 2. Okay. So is this okay? So we can initialize the whole data by using this term. But in this case, we have the 2 constant value in here because we have 2 feature, and so 2 coefficient, theta 1, theta 2, and the constant bias is equal to what? Theta 0. Okay. So we can compile the model in order to what? To create the specific features of the what? The optimizer function. Standard stochastic gradient descent algorithm, and the loss function is equal to the what? The mean squared error. Okay? We should give this property to what? To identify the learning process. Okay? If I choose these terms, and then we may have the learning rule with the what? With the derivation of the in my class. Okay? So we should give the some input in what? The X nomination in here, because the MP column stack should be called in here like this one, because we need to feed to model to what? The one single array. Okay? Otherwise we cannot train this network. Okay? One input, because the model feed function is called x, y, epochs 100 and verbose 0. Okay? You may choose the 1 point. One thousandths. Okay? And so if I feed this function, and then we can say that we can feed the whole data. And so this is the meaning of the single array with x1 and x2. Okay, because though we can fit into the fit function only x. Okay. So y pred can be easily predict from the what, the x value in here, total x value. Okay, so the mean square error can be calculated with the mean square error y and y pred value in here, like this one, and so we can print the error values in here. Mean squared error MSE is equal to the what, to MSE 2.f. Okay, and so if I run this code, and then I can show the what, the mean squared error values on these things. Okay, so training process is running, and so the mean squared error is equal to what, 29.03 for whole data. For example, 100 data, it's very small. Okay, for this case. But how can we visualize the 3D objects in here? For example, we can define the visualization in here like this one. Fig is equal to the what, the PLT figure in here, like this one. Ax is the fig at subplot value in here, 111, projection 3D. Okay, and so Ax scatter function can be called x1, x2 and y with the label of the what, data with noise. Okay, and alpha is equal to 0.7. Okay. And then we can create the mesh grid for the what, the regression plane. Okay, x1 plane, x2 plane can be created with what, the MP mesh grid function. Okay, and so this mesh grid function is called the linspace function body in here, 0, 10 and 50. It's the standard calling function for the 3D objects, and MP linspace and 0, 10 and 50. You may not know these things, but in the internet you can find the mesh grid utilization or the linscape function. Okay, this is just for the visualization of the what, the 3D objects in our cases. Okay, and so the x plane is equals to the what, the MP column stack for 1 points in here, and so x1 plane ravel is a function for the single representation of this mesh grid. Okay, and so the x2 plane should also be given for the ravel. Okay, so y plane should contain the what, the model predict, because we should call the model in order to create the y plane, because we should reach this plane in here like this one, and x plane that reshape x1 plane dot shape. Okay, because the x1 plane is in the 2 dimension, and so we should give the shape plane, and reshape function should be given in here because the y plane is in the 3 dimension. Okay, should set it. And finally should give the what, the AX plot surface in here like this one. X1 plane should be given, x2 plane should be given, and y plane should be given. Okay, so CMap is equal to the color of our listings for this, and alpha is set to what, 0.5. Okay, so PLT grid may not use the legend in here, not need to, and PLT show can be called right now. Okay, so if I run this code, see, this plane is our what? The model parameter. Okay? This plane is visualized into what? In 3 dimension. So x1, x2 and bias should be accomplished by using these terms. Okay? Yes. Predicted to all the plane x1 and x2, and so we have a bias, and so in 3D dimension we can model it because in this dimension x1, x2 and the y. Okay, in each region we should give the total nomination at this time. Okay, so when this code should be given in here like this one, the multiple regressions and logistic regression, but for you I suppose I can give some basic introduction in here in the application session. I can create this example, but this example is very similar in the lesson. So class is so late, and then I can show you this classification progress. Okay, this is the classification pi. Okay, and so all this time we have the NumPy, PyPlot and the other platforms should be included at this time, and so we can create some classification data in here by using this one to assigning to the random variation in here. These codes is coming from here represent the generation of the classification data. Okay, I will share this code in my classroom. So this code generates the feature class variable in here. Okay, this so, and then we will write the data frame to the Excel data, classification data, like this one with the previous one. Okay, this is the simple structure and to Excel created, and so feature 1 and feature 2 to NumPy is loaded to X and Y. Okay, the every data is in the range of the 0 and 1 in the Y data. Okay, so we have the 1 class and 0 class in here. And so how can we use the logistic regression or sigmoid function representation, activation function? Firstly, TF-Keras sequential should be given in here. 2 feature in here. The dance with 1 neuron is given in here, but the activation should be equalized to the sigmoid. And so if we are using the sigmoid function, and then we can create the sigmoid representation. 1 divided by 1 plus exponential minus theta transpose times x. Okay, this is the basic representation of the model classification data. Logistic regression. Okay, so the model is equal to the hx is equal to 1 divided 1 plus exponential theta transpose times x. Okay, for each data x1 and x2. Okay, and so this yields the results of 1 and 2, 0 and 1. Okay, and so in this class we should the activation as a sigmoid. 0 to 1. Yes, because the sigmoid can only produce the 0 to 1, not the infinity or the minus infinity. Okay, Kernel initializer is used with what Glorot uniform. This is the standard probabilistic function to initialize the coefficients in here, okay? And the bias is equalized to zeros, okay? This is a simple representation of these things. But we have another compiler model in here. Optimizer is called the Adam optimizer. And so the learning rule is changed in here, like this one, because we should use the cross entropy function in here. For example, we have the J value is equal to the what? 1 divided by minus 1, and total IN is given in here, and we should use the cross entropy function in here in the logarithmic domain, okay? Plus minus yi, okay, times log 1 divided by hxi, okay. This is called the cross entropy function, okay. The cross entropy function is utilized to binary classification problems. If you have the many class 1, class 2, class 3, we may not utilize this first derivation of this rule because it's not appropriate to reach the correct values. If you are using the cross entropy function, and then you can easily set the 0 and 1 value, or sigmoid value, or softmax value, okay? And so if we are using the cross entropy function like this one, and so we should use the Adam optimizer in here, okay? And also we can utilize the standard stochastic gradient descent, but the Adam is more appropriate to use with the binary cross entropy function, okay? So we can fit the whole data in here like this one, model fit with the x, y, epochs 1, batch size is 32. In the next lesson I will introduce the batch size in the neural network application, and we should have the callbacks in here like this one. The callbacks here means that we can create the class in here like this one, and so in each epoch we can use this parameter with the what? With the learn of the accuracy or loss value or epoch value in the what? In the terminal page. And so in each iteration we can analyze the loss function value, accuracy value, or the other parameters by using this term. And then we can predict the what? The R parameter in here. And so in the next code in here like this one, we will draw the simple line to classify our problem. And so if I run this code like here, and so we have two classes in here, and then for example in 100 epoch we reach the 007, and so the accuracy is more better than the previous one, okay? And so this callback function is utilized for these terms, okay? And then our model draw a simple hyperplane like this one, okay? And so at the left hand side of this hyperplane we should call the 0 class, and at the right hand side of this hyperplane which we call the class 1, okay? And the accuracy of this value is if it is 0.795, okay? Yes, but nowadays it's almost, okay? And so I will share this code in here because we don't have time like this one, and so you may use the mesh grid and Ravel function in here, and so we can use the model predict to create a decision boundary in here. But this is the simple logistic regression function of our study, okay?